Hi guys, in this video we will finish up the simple additions handout. And we'll pick up here with reaction of this amide with LAH. This reaction you may expect that H minus adds to carbonyl, electrons up, and then since there's a nitrogen which can leave, we see it leave when we hydrolyze an amide with aqueous acid or hydroxide, that the electrons would come back down, reform carbonyl, and kick off the nitrogen. And that would actually be the same as essentially this reaction here. Now we said that this reaction here with the acid chloride, electrons up, back down, get the aldehyde. That's the same thing I suggested for the amide. Nitrogen being leaving group instead of chlorine. We said that this reaction occurs in the same way, exact same product with an ester is used. So at this point, O minus would come back down, electrons back down, reform carbonyl, and kick off the OR group. OR. Yeah? Well, over here we're going to see something kind of unique and different. All right, these electrons will indeed add here. And by the way, only LAH, or the aluminum hydride. Sodium borohydride will typically not do this. It's a weaker hydride source, right? An amide is a fairly weak electrophile. The carbonyl is only slightly electrophilic, relatively, compared to an acid chloride or even ester. But that would give electrons up. Get to here. Now instead of these electrons here coming back down and kicking off the nitrogen, something else happens. Now again, if it did that, we would get an aldehyde, right? Carbonyl H. Then the aldehyde, we could add hydride again, and we'd end up getting an alcohol. But here you don't do that. Instead, we're going to end up with this primary amine. Now, how do we get that? At this point, well, what gave up the hydride? Aluminum H4 minus. All right? After it gives up the hydride, it's going to be AlH3. When the hydride is shot out. Well, this aluminum is a Lewis acid, just like aluminum trichloride. And what happens here is the anion oxygen coordinates with the aluminum. And that gives this here, and the aluminum is now minus again. It has 4 bonds, 4 valence electrons. The oxygen is neutral. And at this point, anytime you can kick off a leaving group with a lone pair, make a pi bond, that's easy to do, the nitrogen turns the tables and says, well, I'm going to kick you off, oxygen. A neutral oxygen can be kicked off in this fast step. It's made neutral by complexing with the Lewis acid that's generated after it serves as a hydride source, and that will give double bond to N, 2 H's, and that's a positive charge. Now, a lot of books will just show one more step to get here. A hydride, a second hydride. Okay. By the way, what's going to be the leaving group? O, Al, H, H, H. It's actually double minus. But maybe it doesn't become double minus because right here, this may act as a hydride source again before the oxygen gets kicked off. LAH can actually act as more than one equivalent of hydride. But at this point, I'm going to take care of the proton because I have something that looks like aluminum hydride. These electrons come and take an H. These electrons stay here, and that will give that there. Plus oxygen something like that. This is eventually going to be treated with water. It's eventually going to become aluminum hydroxide. But this is an imine. We haven't seen it yet in lecture, but we've seen it in lab. It's a carbon double bond N. And now another hydride. These electrons, this is polarized double bond, a lot like a carbonyl. These electrons add to this pseudo carbonyl. Instead of C double bond O, it's C double bond N. And this gives okay, there are now 2 H's on this carbon. I'll draw them in. They're there. All right, this is in step 1. We need H2O workup. If we throw in some H2O, this can take an H, and we get our final product. So, instead of this reforming and kicking off the nitrogen, it doesn't do that. Well, nitrogen's not a great leaving group. It could. It could. It does that when we do a base hydrolysis of an amide. But we know it doesn't because we know this is the final product if you do this reaction. So we have to speculate that this oxygen, clearly it gets kicked off. Well, you don't want to come in here and kick off a negative oxygen. That's just probably not going to be done, even in this fast step. But we do have this Lewis acid. And if we complex the oxygen with the Lewis acid, it becomes neutral. Then we can use the lone pair to kick it off. Many books will then show a hydride coming in here, moving these electrons over, and giving the final product. I don't like that because right here, this looks acidic. Nitrogen is protonated. These hydride sources are going to take this H, go neutral, then the hydride can come in. Okay? We had to take care of the proton. Ultimately, this is a very unique reaction. The fundamentals are here in terms of understanding the mechanism. In terms of a product, We are deoxygenating the amide. That's what this does. You remove the oxygen and replace it with two H's. To give an amine. All right. Again, sodium borohydride does not do this reaction. It's too weak. Only LAH. This reaction also works with secondary and tertiary amides. The example I give here is, of course, a primary amide. Okay, let's look at a couple of reactions of nitriles with hydride reagents. If you react a nitrile with LAH, you can reduce it. And what you will get here is the primary amine. Because, keep in mind, this is a C triple bond N. Now, it actually may make more sense to you, based on a previous reaction, the nitrile being reduced with hydrogen, okay, and something like nickel or palladium, okay? That would be just like if we took an alkyne. We learned in Organic 1, we would reduce the carbon-carbon triple bond all the way down to the alkane. And so the carbon-carbon bond becomes a single bond where it was a triple here. Same thing here. The carbon N triple bond becomes a single bond. Okay? So, cyano groups can be hydrogenated just like alkyne groups can be. Now it turns out that LAH gives the same exact product. This is a hydrogenation mechanism. The two H's are coming in syn addition. With LAH, it is a ionic mechanism where the H minus does a nucleophilic addition to the cyano group. All right, we can do that completely. If you like, I would expect that you should be able to do that. We will want to keep in mind what we did up here with that aluminum hydride that's formed along the way. So after my hydride addition, which I showed here, that would give that there, plus aluminum hydride, or AlH3. Probably don't really want to call it hydride. But this can complex here. And we can get to this. Now the nitrogen's neutral. And this probably shoots off another hydride. Okay, the aluminum wants to get rid of it. I'll just, get shot off. I'll use one. At this point, this can come in again, polarized double bond, and we can move electrons here. Now that carbon has two H's, and the N, something like this, it's now minus again. That's kind of in step one. Okay, what is step two? Well, again, with H2O workup. You throw this in water, it's going to hydrolyze this and protonate the nitrogen, and you will end up with CH2, and then that becomes NH2. And there's your primary amine. Okay. I would think at this point we're getting closer and closer to you being able to come up with something like this. I'll do it for you. You'll say, wow, yeah, that was probably pretty straightforward. We throw in some water. This anion can protonate. Yeah. Okay. The aluminum doesn't have an octet. Water or hydroxide. Okay, we formed hydroxide here. Hydroxide can add to the aluminum. I'm just going to call this RNH. Aluminum HHOH. Aluminum is minus again. At this point, it depends on how you take care of the proton. We really don't have any acid, probably wouldn't protonate this, but what if the aluminum just tells the nitrogen to take a hike? Get this here, and then we could use another water, and this takes an H, and there you go. Okay. The aluminum probably has double bonding here, so this could maybe move in here and kick that off, almost like a carbonyl type formation. It gets a little complex, convoluted, a little bit fuzzy, vague here. Okay. Push your way towards where you need to go. Basically, I told you that adding water here will give you your primary amine. Let's go back. Again, hydrogenation is more straightforward, just like alkyne. Triple bond becomes single bond, primary amine. Just kind of know that LAH gives the same product. It's going to reduce it. Hydrogenation is a reduction. But LAH, adding these H's by hydride mechanisms, is also a reduction. Now if we use diball H, okay, let's make this triple bond N. It will add But what do we expect from diball H? There is a difference. Now this can get protonated or something at this point, okay, with H2O workup. Basically it's only going to add once. You can maybe make an argument that shouldn't this complex with the aluminum? Yeah, but it just only adds once. It's not like LAH. And at this point, when we add in H2O, we're just going to protonate this. Okay. And this here is an imine. Okay? We showed it above. Carbon double bond in. Carbon double bond in. An imine is analogous to a carbonyl. Okay? If under the key there was an oxygen, that would be a carbonyl and this would be an aldehyde. But if it's a nitrogen, it is known as an imine. Now the nitrogen, since it's trivalent, is going to have something bonded to it. It can be an H, but it can also be an R group. This here can also be an R group. If that was an R group and under the key, that would be a ketone. But if you change the oxygen of a ketone to a nitrogen, it becomes an imine. That imine nitrogen can have an H or an R group itself. But we get an imine here. Now that's actually not the final product, because with water, we're going to end up with imine hydrolysis, particularly if we include acid. And that is going to be test 4 chemistry. All right. We're going to leave here. Stop there. When we cover this during test 4, I'll remind you of how we got up to this point in this reaction. All right. These are some fairly unique reactions here, okay? Pushing towards just sort of memorization, but you want to find the fundamental understanding, okay? And the consistencies in our mechanistic thought. Okay, these down here were for homework. We'll work these in class. Why don't I work one here? Just got a Grignard. Okay, this is going to be a phenyl minus. These electrons add here, electrons up. That's going to give, I'll draw out the rings just so there's no issue with that. Minus, methyl, and another ring. Game over. There's no leaving group here. You're not going to reform carbonyl and kick off a methyl or a benzene ring. You could kick off a chlorine, an oxygen, or a nitrogen, all right, but not a plain carbon. Until we see some very unique carbons, and those won't be plain carbons. We just have to have H plus workup or water workup. And the product here, now I'll abbreviate these 2 benzene rings to show you both ways. We've done it plenty before, but just in case we need to clarify, that's going to be, I'll put the methyl in the middle just because, why not? That carbon is not chiral, so we don't have to worry about any stereochemistry there. We're going to get that tertiary alcohol. That should be pretty straightforward. All 4 of these should be pretty straightforward. You can also please answer the question here to synthesize tramadol. We also had the question at the beginning here. Why don't I do one of those here? Okay, 3 different ways to make this compound by an addition. Why don't we back this up to, what about back it up to that aldehyde. Okay, because there is an H on that carbon. And react this with methyl magnesium bromide. Followed by H2O workup. That would give that product there. So that is a simple addition to a carbonyl carbon. There's 2 other simple additions. Please make sure you can show those. We'll look at them in class. Finish this up. We looked at this briefly before, but this is a redox cycle, a biochemical redox cycle, estradiol. It gets the OH here, the alcohol group, not the phenol OH. The alcohol OH gets oxidized to the ketone. That compound is known as estrone. And then if you come back this way, that's a reduction of the ketone back to the alcohol. Now in lab, the reduction, we would use a hydride reagent, but your body uses, as a hydride reagent, NADH. And as an oxidant, it doesn't use one of the big 3. It uses NAD+. Okay? Now let's look at that. Here is NAD+. It's got this structure with this pyridine ring, and in the pyridine ring, nitrogen is positive. All right? Okay, it is an oxidant. And the NADH, it's got an added H because look, this ring has 1 H here, but this has 2 here. And so because of that, we add the H to the name. Over here, because of the positive charge, we have that. Okay. Clarifiers in the name. Okay, this is your hydride source, biochemical hydride source. How this works is these electrons move here, these electrons move here, and kick off an H and the 2 electrons. Kick off a hydride. Just like sodium borohydride kicks off an H-. Well, it's not exactly. Here we have pi electrons, okay? And the driving force here, why would this kick off a hydride? Usually H is not a good leaving group. Well, a few unique cases it can. Okay, this is a very unique case. Don't start going around having H's be leaving groups. What's a driving force? This ring becomes aromatic. All right. Now if we go from here to here, that's a reduction because we added an H. Remember, anytime you add H's, that's considered a reduction. If we come this way, we're removing an H. That would be an oxidation. But the oxidized form acts as an oxidant. The reduced form acts as a reducing agent. The reducing agent has the H. It's in the reduced form. Okay. Now here's another biochemical example of redox. Pyruvate has two carbonyls. One is a carboxylic acid, the other is a ketone carbonyl. The ketone carbonyl is reduced by NADH. All right, NADH reduces this. Okay, so it gets reduced. NADH gets oxidized to NAD+. Now if you go the other way, NAD+ will actually oxidize this alcohol to the oxidized form, and the NAD+ will become the reduced form. So it can go both ways. All right. Now this is showing an abbreviated structure. The full structure is here. Okay. And this up in here is, it's kind of flipped on you. Here's the primary amide. All right. And it's right here where this takes on another H. So it's flipped upside down. And the ribose, this is a ribose 5-membered ring. And then it's leaked through here, phosphate linkages, okay, to ADP. There's a fairly large molecule. You'll learn these types of things in biochemistry. But that portion right there comes from niacinamide, which I believe is like vitamin B2. Is that right? No, it's vitamin B3. Vitamin B3, okay. Or that's niacin. Not sure of the chemistry there, if the acid is converted to the amide in the body, but that acid, pyridine and the carboxylic acid at the 3 position is niacin or nicotinic acid, and that is actually a vitamin because your body needs it, and this is one of the main reasons why it needs it. Okay, so be familiar with the NAD+, NADH redox system that your body uses. Okay, you can also see that with the enzyme HMG-CoA reductase, which reduces HMG-CoA. All right. It reduces the thioester. Hydride adds up, down, kicks off the sulfur, and then adds again. That's how you get the primary alcohol. Okay. That's the new functional group. And the reducing agent here again is NADPH. You need two equivalents. Okay. That's just like we did over here. Okay. Get the primary alcohol. This is not an acid chloride, it is a thioester. Same chemistry though. Okay. Eventually this is converted to cholesterol in your body. If you inhibit this enzyme and inhibit this transformation, you will inhibit the biosynthesis of cholesterol. That's why there's the cholesterol-lowering drugs. A lot of them target the HMG-CoA reductase enzyme. All right. The NAD plus and H are not actually enzymes. These are considered cofactors. or coenzymes. Okay, a little bit of biochemistry there. Back is some applications. Okay. Very last step here, synthesis of Allegra. We've got this ketone, and it's being reduced with sodium borohydride to the alcohol. All right. And of course it's racemic because we talked about that. The hydride adds either from the front or back. That is a chiral carbon. So there's an example of using hydride source to reduce a carbonyl in a drug synthesis. Okay guys, that finishes up this handout here. Simple additions to carbonyls and nitriles.